Okay, so one thing that I forgot to mention is how to integrate to find the volume of a solid of revolution when the axis of revolution is offset. When it's not just the x-axis, y equals 0, or just the y-axis, x equals 0. Sometimes it might be something slightly different. But for purposes of completeness, I'll do the x-axis and y-axis anyways. Okay, so let's start by drawing the region that's going to be revolved. Let's start with a coordinate plane, just a little one here. Okay, let's make this one blue, this one green, and this one red. So there should be three curves that sort of form the boundaries of our region. Y equals the square root of x. That's just a square root curve. It's going to be shaped sort of like this. Well, it probably doesn't need to go that far. Y equals 0. That's just the horizontal line at, that's just the x-axis. And the line x equals 3 is going to be a vertical line at 3, which should be, let's see, square root of 3 is about 1.7. Let's just say here. Okay. So I guess technically speaking, these should have little arrowheads on them, but the region to be integrated is right here. Sure. Or rather, the region that's going to be revolved, right? And we're going to use integrals to find the volume of those solids that result. That area is right there. Okay. So let me write some of these. Let me write the names of some of these curves. Okay, so this green one we know is y equals 0. This red one, x equals 3. And this blue one, y equals the square root of x. Or you could also call it x equals y squared. And you can do that just by solving for x, just by taking that and squaring both sides. And depending on whether you're doing, whether you're having to do the integration dx or dy, one of these, might be preferable above the other. Okay, so some more important things. This point of intersection is 3 comma square root of 3. Yeah. So this point is 3 comma square root of 3. Which means that this is the square root of 3 over here. This is 3, as we probably know. This is the point 0, 0. No kidding. And this is the point 3 comma 0. You could probably tell that as well. Okay. So first, let's integrate this with respect to, let's revolve this around the x-axis. Okay. Okay, so what that means is, let me just steal this here. Oh, that sort of copies the whole thing, doesn't it? No, that's no matter. Okay. So I'll draw a simplified version of it. So this is sort of our region right here. And it's going to be revolved around the x-axis, this horizontal line. Which means that's going to form this sort of bullet shape. Now, we're forced to do this using the disk method. So what that means is that okay, so what that means is that our disks, right, our slices, the way we slice this up is going to have to be like this. Because as you remember, disks are parallel, disks are perpendicular to the axis of revolution, right? And our axis of revolution is horizontal, so our slices or our disks must be vertical. And so that'll be dx. Okay. So because this is dx, our integration is going to go from an x value to an x value, specifically 0 to 3. So x equals 0. So first the pi, right, for the disk, x equals 0 to x equals 3. And let's see, it's just going to be straight disk, no washer. Okay, so with respect to our axis of revolution, which is the x-axis, the, the curve, right? The curve is y equals square root of x, right? We want y equals square root of x and not x equals y squared because we're doing this dx. We want everything in terms of x. So our big radius is square root of x squared. And we don't have a little r. We don't have an inner radius because, well, our shape is right next to the axis of revolution. If you wanted, you could have a little r, but it would just be 0 minus 0, or well, it would just be 0, right? For y equals 0. So no need to include that. Okay, so this resolve the inside. Right, square root of x squared is just x. Integral of x dx is x squared over 2, so that's pi times x squared over 2, evaluated at 0 and 3. So plugging in 3, we get, let's keep that pi on the outside. We get, so plugging in 3, we get 3 squared, which is 9 over 2. Plugging in 0, we get 0 squared over 2, so 0. Well, I guess for neatness, maybe put parentheses around these. Doesn't really matter right now. But that ends up being 9 over 2 pi. And obviously you can adjust this to your numbers. Okay, so second, just revolved around the y-axis. Okay, so again, drawing this, what's going to happen here is this shape is going to get revolved around the y-axis, like that. And so the shape that that's going to form is this weird sort of on the outside, it'll be a cylinder. But on the inside, it's just going to be a series of curves that sort of come into, to meet at a point. If that makes any sense. Yeah, I can't think of a real life shape that's like that. Okay. But, knowing that we're revolving around the y-axis, and that for disks, our slices are perpendicular to the axis of rotation, those slices are going to be horizontal, which means that we're going to do this dy. Okay. So we set up the integral. In terms of y, our shape goes from a y value of 0 to a y value of square root of 3. Okay. Relative to the axis of rotation, which is the y-axis, we do have a big R and a little r. We do have an outside radius and an inner radius, right? So rather than just being disk, this will be the case of disk where we have a washer. So the washer method. So our big R, the curve that's further away from the axis of rotation, is going to be hold on for 1 second. That's right. It's going to be x equals 3, right? And although that doesn't sound like it's in terms of y, it really is, because when a function is in terms of y, you can write it as x equals. Just like when a function is in terms of x, which you're familiar with, f of x, right? You can rewrite f of x as y equals. When you're in terms of x, all your functions can start with y equals. Just the same when you're in terms of y, all your functions can start with x equals. So our outer radius is this curve, x equals 3, right? So just so what we'll write is of course just 3. So that'll be our big R minus our little r. Well, what is our little r? It's this blue curve. And that blue curve is, in terms of y, it's x equals y squared. So put a y squared right here. Okay, and we're going to do this integration dy. Okay, so resolving that a little bit, y 0 to square root of 3 of 9 minus y to the 4th dy. Okay, then that will just be pi times, if we integrate that, we're going to get 9y, remember we're integrating dy, minus y to the 5th over 5. Okay, evaluated at 0 and at square root of 3. Okay, so keeping the pi outside, when we plug in square root of 3, what do we get? We get 9 square root of 3 minus square root of 3 to the 5th over 5. And when we plug in 0, we get 0 minus 0. Okay, so we don't really have to think too much about that. Okay, about how to resolve this. 9 square root of 3 can stay that way. Now with square root of 3 to the 5th power, an easy way to think about it is you have 5 copies of square root of 3, all being multiplied together. That's what being to the 5th power means. So you can sort of imagine this. You don't actually have to write it out. So this is what you have. This is going to be, multiply, take two of them out and make yourself a 3. Take two more of them out, make yourself a 3. There's no other one to go with this one, so what you end up having is 9 square root of 3 on the top. So we have 9 square root of 3 over 5. Okay, if you want to factor out the square root of 3, you can. If that makes it easier to do this part. 9 minus 9 over 5. Let's see, 9 is 45 fifths minus 9. That should be 36 fifths. So what we end up with is 36 square root of 3 pi over 5. Right, there's that 36 fifths times the square root of 3 and the pi that were outside. Okay, now we're going to do a slight variation on this, where our axis of rotation is still vertical. It is just not exactly the y-axis. Let me erase this. Okay, so I'll do it over here just so you can see this and the last one side by side. So revolved around the vertical line x equals 3. Okay, so what that looks like is the axis of rotation is actually right here. And the shape is going to be swept around this this vertical line, which is going to result in a sort of inverted bowl shape, maybe like a very flat bullet. Okay. Axis of rotation being right there. Yeah. Okay, so the way to deal with an axis of rotation that isn't, one of your, one of either the x-axis or the y-axis, is you have to modify this this formula a little bit. Okay, so since this is a vertical axis of rotation, our slices are going to be horizontal since we're using disks. Right, for disks, our slices are perpendicular to the axis of rotation. And so we're still going to be doing this dy, right? Which is why, I want to compare it to the one immediately previous. Okay, so the shape still goes from y equals 0, right? Still want everything in terms of y. Still goes from y equals 0 to y equals square root of 3. Still going to be doing this dy. And we're still going to have an outer radius minus an inner radius. Well, an outer radius squared minus an inner radius squared. Okay. Now, with respect to the axis of rotation, which is now x, this vertical line x equals 3, the outer curve, right, the curve that's further away from the axis of rotation, is this sort of x equals y squared, and we're going to have to write it that way again because we're doing this dy. So x equals y squared is our outer radius. Let's put y squared right here. And our inner radius is still x equals 3. Now, this is where things get different. Because our axis of rotation is offset, we have to throw in a minus 3 here and a minus 3 here. Because this is our axis of rotation. So let me also just mark that in red. Oops. And here too, just to know, just so you guys know where that comes from. So we subtract our axis of rotation from each of these curves. I guess I could stop explaining there, but what you're essentially doing is by subtracting the axis of rotation, the value of the axis of rotation from each curve, you're essentially shifting the whole shape and the axis of rotation. You're basically shifting everything to the left in this case. Sometimes it'll be left, right, based on where the axis of rotation is for a vertical axis of rotation, or you'll be shifting it up, down for a horizontal axis of rotation. I mean, you don't need to know that that's really what's happening, but if you straight up drew y squared minus 3, let me draw it over here. If you straight up drew y squared minus 3, what that would look like is it would look quite like, let me do this in a slightly different blue, it would look quite like what you already have. It's just shifted to the left by 3. And this bottom side doesn't really matter, but it would be there. And so this is our sort of pretend curve, x equals y squared minus 3. And 3 minus 3, well, that's just x equals 0. Which would be here. And we still have the same curve here. So our shape essentially becomes just the same shape, just over here. So what subtracting the axis of rotation from each of the outer and inner curve does basically is it shifts everything just so that the whatever your axis of rotation is essentially coincides with either the x-axis or the y-axis, depending on which way your axis of rotation is facing. So you see, by shifting all of the curves to the left by 3, the axis of rotation now coincides with our y-axis, and it's sort of like once you subtract the 3, it's basically like you're doing this integration where everything was all lined up to begin with. But anyways, all that stuff is sort of beside the point. You don't have to have that understanding of it. You can just, write down in your little notebooks when the axis is offset, subtract the value of the axis from each curve for the disk method. But that is essentially what it's doing. It's shifting every curve so that the axis of rotation lines up with one of your coordinate axes again. Okay. So, oh, right, and I guess technically speaking, why don't I do that. Right. Okay. Yeah, I guess I could flesh this out a bit more. Well, I don't need to. Okay. Anyways, that's not what you're interested in. Okay. So this is just know that this is 0, and we'll just be ignoring it. Okay, so pi times the integral from y equals 0 to y equals the square root of 3 to, if you simplify this, y squared minus 3. Hopefully you remember the rule for just squaring a binomial. It's the first thing squared, so y to the fourth. And then the next term is 2 times the cross product, because you have 2 of those cross products. So minus 6y squared. And then the square of the last, the square of the second term of the binomial, so plus 9 dy. Right? This disappears because it's 0. Okay, so we integrate that. That ends up being pi times y to the 5th over 5 minus 6y cubed over 3. So 6 over 3 is going to be 2y cubed, yeah, plus 9y dy. Oh wait, no, that's integrated. I don't need the dy anymore. I need that evaluation bar. 0 to the square root of 3. Okay, so very much like the like this over here, we're gonna have to deal with some things. So pi times, plug in the square root of 3, we get the square root of 3 to the 5th over 5 minus 2 times the square root of 3 cubed plus 9 times the square root of 3 minus 0 minus 0 plus 0 for when you plug in 0. Okay, so pi times, okay, so square root of 3 to the 5th, right? You can take out 2 of those, that's a 3. 2 more, that's another 3. You're left with a square root of 5, square root of 3. I mean, we're left with a singular square root of 3, so that's going to be 9 times the square root of 3 all over 5. Okay, for this middle term, you can take out 2 of those square roots of 3. You get yourself a 3. So that's going to be minus 6 times the the remaining square root of 3, and then plus 9 square root of 3. If you want to make it easier to look at, you can factor out that square root of 3, and that's just 9/5 minus 6 plus 9. Okay, so I guess I should have equal signs here. Okay, so that's pi times the square root of 3 times, okay, so first just combining the easiest terms, -6 and 9, that makes 3. Okay, 3 is 15/5. 9 plus 9/5 plus 15/5 should be 24/5. Okay, and just rewriting that a little bit, 24 square root of 3 times pi all over 5. Okay, and now the last best one. Again, a vertical axis of rotation. We're going to revolve this shape around the line x equals 6, even further away. Okay, so what that's going to look like is, what colors do we use? Blue and red. Okay. Blue with this. Red with this. And our axis of rotation is going to be approximately over here. Okay, and we're going to rotate this shape sort of around this axis of rotation. Okay, so the shape that that's going to form is going to be this weird sort of failed bundt cake looking shape. This weird curved volcano. I guess I can finish that out. More or less, yeah. It's just got this weird cylindrical core cut out of it. This is the sort of interior. So it's got this sort of curved outside and this sort of straight-walled cavity coming in through the inside. Okay. So let's see. So since our axis of rotation is, again, vertical, our slices, and we're doing this by the disk method, which is the only method we know right now, our slices are going to be perpendicular or horizontal. So again, just like the last two, we're going to do this dy, and feel free to compare this with the last two, all the same. Okay, so our axis of rotation is x equals 6. Okay. Our curve is x equals 3 right here. And in terms of y, our curve is x equals y squared right here. Okay. So our integral is going to go from 0 to square root of 3, just like the previous ones, right? That's, that's where our y goes from and to. And just like before, we're doing disks, dy. Okay, and we're going to have a big radius minus a little radius. Now, again, relative to the axis of rotation, our outer curve is this x equals y squared. So throw in a y squared here. And our inner radius is that x equals 3. So I'll throw in a 3 here. Now our axis of rotation is x equals 6. So what I have to add is a minus 6 here and a minus 6 here. And again, if you look at this a little bit, this is going to be negative 3. And so what it sort of represents is shifting everything to the left by 6. And so you sort of see if you do that, what you get is y squared minus 6 would be down here. You'd have x equals negative 3 down here. And so, you've got your shape. You basically shifted your shape to the left by 6 units and your axis of rotation also by 6 units. And so now you're just sort of taking the shape and you're rotating around here. So, it looks very much the same, except this is now, everything's been shifted to the left by 6 and you're essentially, functionally revolving around the y-axis. is what that -6 is doing. But you got to add in that -6. You got to subtract your axis of rotation if your rotation is offset. If your axis of rotation is offset, and technically speaking, you could do it even when your axis of rotation is the y-axis or is the x-axis. It's just that you'd be subtracting 0, right? Because the equations of those are like x equals 0 and y equals 0. So you're actually just subtracting nothing. You're literally shifting to the left by none, 0, and so it doesn't really appear. But it's this isn't a special case. It's true in the general sense. Is sort of what I'm saying. You just don't see it in the cases where you have a nice axis of rotation. Okay. Anyways, after you set this up like this, it's just sort of standard stuff. 0 to the square root of 3. Okay, so I'm gonna run through this kind of fast. That's gonna be y to the 4th minus 12y squared. Right, because that's -6. Yeah, okay. Plus 36. Minus, okay, this is going to be -3 squared, so +9 minus +9 minus +9 dy. Okay, and I figured the least I can do is combine that 36 and that -9. So we have y to the 4th minus 12y squared plus 27 dy. Okay. All right, so let's keep on going. Pi times, well, we can integrate y to the 5th over 4, or y to the 5th over 5, I mean, sorry, minus 12y cubed over 3. 12 over 3 is 4, so minus 4y cubed plus 27y, evaluated at 0 and square root of 3. Okay, almost there. Let's keep that pi on the outside. So what we're going to have is, let's plug in square root of 3. Square root of 3 to the 5th over 5 minus 4 square root of 3 cubed plus 27 square root of 3. Okay, that's for plugging in square root of 3. For plugging in 0, we're going to get 0 minus 0 plus 0. Okay, we'll do the same thing with the square root of 3 to the 5th power. 2 of those becomes a 3, 2 of those becomes another 3, and we have 1 left over, so 9 square root of 3 over 5. Okay. For the middle term, 2 of those square roots of 3 are going to become a 3, so we'll have minus 12, and then a square root of 3 left over, plus 27 square root of 3. And then all the rest is, nothing. If you want, you can factor out that square root of 3. You're going to get 9/5 minus 12 plus 27. Okay. Just combining that minus 12 and that 27 first, that's 15. 15 is 75/5. 75/5 combined with that 9/5 is going to be 84/5. So square root of 3 times 84/5. And, just rewrite that 84 square root of 3 pi all over 5. So that's going to be your volume there. So that's the end of it. This should be pretty similar to your number 4. And you're gonna see problems where you have to revolve a shape around an offset axis. In your other problems as well. But this is almost up to some maybe some arbitrary constants and your problems identical to number 4 on your homework. So just remember, if you have an offset axis, subtract it from each curve in the disk method or the washer method. Instead of big R squared or little r squared, remember to have big R minus the axis of rotation all squared and little r minus the axis of rotation all squared.